he moved to the United States for his postdoctoral studies. There, he utilized Raman and ultrafast spectroscopy to study the excited state symmetry of semiconductor nanocrystals and charged interfaces, respectively. In 2026, he joined Adelaide University, Australia, as a lecturer. His current research interests include the synthesis of novel semiconductor nanocrystals, spectroelectrochemical studies of electrified interfaces, and photoelectrochemistry of semiconducting and plasmonic nanocrystals. Okay, we are honored to have you, sir, for this afternoon. Over to you, sir. Hello, we request you to switch on your camera. Dr. Arun, can you hear us?
Hello. Hello.
Hello.
Yeah. Can you hear? No.
Welcome. Hi. I hope I'm audible. Okay, anyway, I'll start. Let me share my screen. Can you see my screen? I hope you can see my screen. And my name is Arun. Maybe the people have introduced me. Uh, but before that, first of all, thanks to all the organizers for inviting me for giving a talk at this conference. So today I'm going to talk a bit about my research and a little bit background before that. Uh, so title of my today's talk is dissecting nanocrystals with electrochemistry and spectroscopy. So there are a few terms here. First one is nanocrystals, then electrochemistry and spectroscopy. So I'll be giving more importance to nanocrystals. Uh, okay. To sum up, this is my research interest. It's basically on I like to synthesize new nanocrystals, especially quantum confined semiconductors and plasmonic nanocrystals, which I'll talk in detail in my talk later, and then use electrochemistry to manipulate their optical and structural properties, and also use light to induce some current flow and potential changes in nanomaterials so that we can use these materials for catalysis. So as I mentioned, my interest is in nanoscience. Most probably you have, not many people have heard about, especially the students might have heard about nanoscience, but you guys have definitely heard about nanotechnology. So uh, there are few figures here, and you guys might know few of these guys. So basically, nanoscience is the study of the properties at nanoscale. Uh, it's been there for a long time. So if you see this picture, it's called a Lycurgus cup. It's made by Romans. Uh, the property of this material, this glass, is that it exhibits two different colors when you shine light in two different directions. Uh, and later in the reason for these two different colors is because these glass are embedded with small nanoparticles of gold and silver. Later in 1857, uh, this famous scientist, his name is Michael Faraday, if you guys don't know. So he synthesized a small gold nanocrystal solution. And from there onwards, the nanoscience started, the field of nanoscience started booming. But in the case of nanotechnology, which is more familiar to you guys, uh, strictly speaking, it's the ability to manipulate single objects. So basically, the difference is that word single. So in nanotechnology, if you can manipulate single object at nanoscale, that's basically nanotechnology. So this guy, Norio Taniguchi, he came up with the word called nanotechnology, and probably you might have heard what Feynman said. There is a plenty of room at the bottom of the room, which is kind of like a prediction for the field of nanotechnology. Uh, so my interest is in nanoscience. Basically, I study the properties of matter at nanoscale. So when I say nanoscale, we need to define what is nanoscale. Basically, nanometer. What is nanometer? It's basically 10 raised to minus 9, 10 raised to minus 9 meter. Okay. So as you can see, this is a bulk gold. It's like one kilogram of gold. It's warm. Gold and yellow in color. And if you reduce the size to these wires, it's still yellow. If you make yellow, but when you go to nanoscale, when you make tiny gold nanoparticles, it's not uh, that yellow golden color anymore. It's actually pink, uh, pink color. So the reason why this is pink color is because of some plasma resonance, which I will explain later. But the most important thing is, when you make a nanomaterial, or when you say something about nanomaterial, when you're researching about nanomaterial, the most important thing is to ensure that your nanomaterial is showing something different from your bulk material. If there is no difference in properties, then there is no point on doing nanoscience on that material. Okay. There are two important properties we need to consider when speaking about nanomaterials. Why they are different from the bulk solid. So one is the changes in the electronic structure. So let's assume we have an atom. And in an atom, we have uh, or molecule, we have a HOMO and a LUMO. Okay, and we combine these atoms to form molecules, and molecules, more molecules to form nanocrystals. And you can see that you have discrete energy states at the band edges. When you add more and more atoms to the nanocrystals, you will form basically bulk solid. Then you don't have this discreteness. You only have a continuum of energy states. So basically, in nanoscale, you have some discrete energy levels at the banded states. The second property is a bit more interesting. Most of you guys are familiar with this image. So you want to dissolve something. Uh, let's say you want to dissolve sugar in water. So what's the best way? You can either stir the solution or you can make the powder. So we are not doing the stirring. We are only doing the just adding the powder. So what happens when you add the powder? So you're making it very, very small. So what happens when you make it small? So basically, when you make it small, you have large number of atoms on the surface, and also you have a large surface area compared to its volume. So basically here, on the left hand side, you can see that as you increase the size of the cube, the surface area to volume ratio decreases. And here, in the case of a sphere, you can see when you increase the radius, the number of atoms on the surface reduces. So what does this basically means? Basically, it tells us that you have a lot of atoms on the surface when you go to very, very small size regime, basically nanoscale. So these are the two important properties which usually you will observe when you go to nanoscale. The evolution of your electronic structure, and also the surface area and activity. When you have more number of atoms on the surface, you basically increase the activity. You can interact with more adsorbates or solvents, and you can do a lot of catalysis and those kind of stuff. Uh, so far I have talked about the properties of nanomaterials. So how do we make these nanomaterials? So there are two ways, two approaches basically. First one is the top-down synthesis, and the second one is the bottom-up synthesis. As the name suggests, in top-down synthesis, you start from a big material and you slowly uh, use some physical methods to etch away small nanoparticles. So basically, use ball milling, physical vapor deposition, and those kind of physical methods. So most of the cases, physics people or physics basically use top-down synthesis. In the case of bottom-up synthesis, you start from the molecular precursors. You want to make a nanomaterial, so then you take the corresponding molecular precursors and you react them and slowly form your nanomaterial of interest. So basically, it's just like cooking. That's why this mean is there. As chemists, we basically use bottom-up synthesis. We start from molecular precursors and then use traditional solution phase chemistry to make these nanocrystals. We can make metallic nanocrystals like gold. We can also make semiconductor nanocrystals, perovskites. We can also make insulators like silicon nanocrystals. So we can make different type of nanocrystals using this bottom-up synthesis, as well as the top-down. But as chemists, we only focused on bottom-up synthesis. So in this talk, I'll be speaking about some plasmonic semiconductor nanocrystals. So before going to that, I'll just introduce. Sorry. So when you do the bottom-up synthesis, as I said, you'll get nanocrystals, and this is how it looks like. You'll have a core of that material of interest, and you also have these fine fibers. So basically, in the nanocrystal, bottom of nanocrystals, you also add something called ligands. Ligands are basically organic moieties or inorganic moieties, which actually stabilize the nanocrystals. Because inside the nanocrystals, your atom is coordinated each other, but at the surface there will be uncoordinated atoms, so there will be a lot of energy. So you want to stabilize these nanocrystals. So to stabilize those nanocrystals, we add some Lewis base, which can donate electron density to the uncoordinated atoms. So basically, ligands coordinate to the nanocrystals. So they stabilize the nanocrystals, and also they prevent aggregation between the nanocrystals. If you don't have nanocrystals, you got charges, and they will attract each other, and yeah, so they will aggregate. So you don't want to aggregate the nanocrystals, and these ligands also determine the solubility of your nanocrystal. Suppose if you want to dissolve in water, you can change the ligand in such a way that there will be hydrophobic interaction on the ligand, between the ligand and the water molecules. If you want to dissolve in organic moiety, you can also use long alkyl chain ligands. And another interesting thing is, as I mentioned before, in nanocrystals we have this discrete state just close to the band edge. In addition to that, you also have trap states, something called trap states. These localized states are called trap states. Trap state can arise from a few different things. When you make these nanocrystals, basically they are ordered solid, but there can be, some defects which you might have known before where we have studied. That can happen. They can create some intermediate energy states between the conduction band and the valence band. And also, as I said, there is a lot of surface atoms, and you all the surface atoms because the surface atoms are stable. So this can also create trap states. And finally, you deliberately add some electro atom to create these intermediate state. These are called dopants. You might have heard about it. So basically, this is what usually happens in semiconductors. Uh, there are two different type of semiconductors. First one is a direct band gap semiconductor. An example is gallium nitride. Here, your conduction band minimum and valence band maximum, they are at the same momentum k vector. In the case of indirect band gap semiconductor, the valence band maximum and the conduction band minimum, they are not on the same k vector. And classic example is silicon. Silicon is an indirect semiconductor. So the interesting property is that when they interact with light, the electron in the valence band, it will get excited into the conduction band and form an electron hole pair. Basically, hole is a vacancy of electron. So this electron hole pair is coulombically bound. This continuum of states, but at the when you go to nanoscale regime, there are discrete energy levels, and we can correlate the band gap of the nanocrystal with the bulk using this equation. And you might be familiar with this. This looks similar to what you have studied in your quantum chemistry classes, particle in a box model. Basically, the radius of your particle, size of your particle, is inversely proportional to the band gap. So basically, when you reduce the size of your nanocrystals, your band gap increases. And there is and this is called quantum confinement effect. And there is a condition for observing or exhibiting quantum confinement effect. Your size of the nanocrystal should be less than what's called a Bohr exciton radius. So Bohr exciton radius, we all are familiar with what Bohr radius is. Bohr radius is basically the most probable distance between a nucleus and the electron. But Bohr exciton radius is something similar, but in the case of nucleus, it's the hole. So basically, the energy, the distance between hole and an electron, that's basically called Bohr exciton radius. So when the size of the nanocrystal is less than or equal to your Bohr exciton radius, you will see the increase in the band gap, and this is called quantum confinement effect. So, as I mentioned before, we as chemists synthesize using bottom-up synthesis. We start from molecular precursors and we react them using traditional solution phase chemistry alongside ligands. We add ligands as well and heat them up to get these nanocrystals. In 2023, these three gentlemen, they got Nobel Prize for making quantum confined with semiconductor nanocrystals, colloidal semiconductor nanocrystals called quantum dots. Unfortunately, Bruce passed away last week. Anyway, so in today's topic, I'll be speaking about plasmonic semiconductors. So I have mentioned about semiconductors. Now I'll briefly show what what this plasmon is. So we know metals, right? We know metals. Metals have, for example, this is gold atom, and you can see there are electrons filled at different levels, and at the outermost level you have the valence electron. The interaction between the nucleus and the valence electron will be very relatively weak compared to the core electrons. So these valence electrons are relatively free, so they are called free electrons. When you combine these atoms to form a bulk gold, you have a lot of valence electrons, and these electrons, free electrons, can oscillate, and this oscillation is called plasmons. So there is a quantization. There is a quantization of these electron oscillations. So that's called plasmon. When you come to nanocrystals of metals, your size of the nanocrystal is confining the plasmon. So the plasmon can't, propagate, unlike what it do in a metal. In metal, it can propagate, but in a nanocrystal, it can't propagate because of the nano size of the nanocrystal. So in such case, these plasmons are called localized surface plasmon resonance. Other than metals, you can also observe this in semiconductor. But traditionally, people use metals for these plasmonic application of these plasmons. Basically, they use gold and silver. They also use copper sometimes. But recently, you want to replace copper and gold because they're expensive. So people are also trying aluminum and magnesium as well. So the interesting property here is the free electron density. So the free electron density is what actually controls the plasmon. So in this case, for metals, the free electron density ranges from 10 to the power 22 to 10 to the power 23 centimeter cube per centimeter cube. And this results in a plasmon frequency in the UV-vis region. For example, here, in the case of gold nanocrystals, you can see it's in the visible region. And the application of these nanocrystals is, these plasmonic materials is that you have free electrons that are oscillating. So it will create an electric field. So basically, when something is near to this nanocrystals, you have a enhanced electric field. So when you have an enhanced electric field, you can do a lot of things. Basically, people have used these nanocrystals to enhance the Raman signal of analyte molecules. So this is called surface enhanced Raman spectroscopy. Sometimes they use these plasmons to carry out catalysis, and sometimes also they use it for thermal labeling, sensing, thermal imaging, those kind of things. The problem here is, so we have metal and they have free electron density, as I said, some free electron density. And this is the maximum you can achieve with these metallic particles. You can't easily change the free electron density in a metal. And you only get the surface plasmon in the visible and UV range. So we want to find materials which we can also use in the near infrared. I'll tell you why the reason in the next slide. So as I said, I will be speaking about plasmonic semiconductor nanocrystals. So traditionally, pure undoped semiconductors don't have a lot of free carriers. If you want to introduce free carriers, that means you have to introduce excess charge. If you want to introduce excess charge, what do? We basically do doping. We add an hetero element. We can add a lot of element. People have already come up with a lot of different combinations that exhibit plasmonic peak or plasmonic resonance. Here are the few examples. And so as a result of doping, the carrier density comes around 10 to the power 21 per centimeter cube. And as a result, the plasmon will be in the near IR to mid IR region. So unlike metals, here, this is not the maximum. So you can still increase or you can still decrease. And so plasmons in these materials are much more tunable. much more tunable. So as a result, we can use these materials in smart windows. You might have seen these things when you press a button, the window faints, and when you press on button, it will get clear. And also, you can use these materials for as electro-optic filters. Basically, you can use some charge to change the transmittance of these materials, and thereby, cutting off some wavelength. So basically, you can use it as electro-optical filters as well. So so we need to create charged nanocrystals basically. So you want to dope these nanocrystals. Either you can add a hetero element, or you can also add some electrons. So how do we dope them? Basically, how do we charge them? So there are few ways of charging these nanomaterials or molecules. The first way is you can use light, but the problem here is when you use light, there is no control, and you can't predict when the charging occurs, and we don't have much knowledge about the energetic information. Basically, we don't know at what wavelength of light, when you shine the light, the charging happens. Uh, then you can also use redox reagents, some reducing agent or oxidizing agent. This can also, introduce some charges, and this is controlled. But at the same time, if you want to increase, for depending on your nanomaterials, you want different reagents. And also, when you react these nanomaterials with a chemical redox reagent, there can be side reactions, and also these are not reversible, uh, easily reversible. Another approach is, you can use electrochemistry. Basically, you can use an electrode, and you can inject electron into the nanocrystal. Since we are using an electrode, we can measure the potential and correlate this to the energy as well. So basically, we can use so I will be using electrochemistry to charge these nanocrystals, so dope these nanocrystals and see whether the plasmons we can tune the plasmons. So when you charge these nanocrystals, you're charging it, but at the same time, we want to observe the plasmon. So what we want to do, we want to combine a spectroscopic method. You can see, you can see here that these are like plasmonic peaks. So if you want to observe them, if you want to see some shift in these plasmonic peaks, we need to simultaneously do spectroscopy. This technique of combining electrochemistry and spectroscopy is called spectroelectrochemistry. Basically, you can combine different spectroscopic techniques with electrochemical techniques. For example, you can combine absorption, emission, magnetic resonance methods, RAM and X-ray techniques, with different electrochemical techniques like photometry, chronoamperometry, potentiometry, impedance. So different combinations. You can try a different one. Professor Theodor Kuvana was the pioneer in this field. He came up with the first experiment where he oxidized this molecule. It's called toluidine to its oxidized form, and simultaneously observe its evolution in the absorption spectrum. So basically, I'll be doing spectroelectrochemistry on these plasmonic semiconductor nanocrystals, and this is how I do the experiment. So I'm charging a semiconductor, so it got a valence band and a conduction band, and you're shining light, so you'll definitely form the exciton. You got an electrode. When you raise the Fermi level of this electrode or apply potential, you slowly start filling the trap state, and even further, you can even start filling the conduction band. This process can go the other way. If I reduce the Fermi level or go to oxidizing potential, we can fill a lot of holes here, and you can do the charging. Uh, and simultaneously, we will do the spectroscopic measurement. So this is the setup I'm going to use. You have a light source, and you'll have a spectrometer. The light will pass through the electrode, and where we do the charging and simultaneously collect the electrochemical data as well as the optical data, and then we basically correlate them to get meaningful information about the process of interest. Regarding the electrode, I'll briefly show the design of the electrode. So this is the cuvette, and its path length is equal to the electrode thickness, so that we can only monitor those species which are charged. So this is the electrode. You've got a working electrode, you got a counter electrode, and you got a reference electrode. So basically, working electrode is where the process of interest is happening. For us, it's the charging of the nanocrystals. Counter electron just balance out the working electrode. And for measuring the potential, we are using the silver wire reference electrode. So if you closely look at the working electrode, it looks like a honeycomb. Basically, it's a cylinder. Each of these holes is a cylinder in three dimension. Yeah. And basically, your nanocrystals will diffuse and collide with the electrode surface and get charged. At the same time, we will shine light and collect the absorbance or scattering or whatever spectroscopic signals we want. So this enclosed geometry of these electrode help us to get faster response. So we are doing all these experiments in solution, and it will be limited by diffusion. So if you have an enclosed geometry, more nanocrystals will be charged and you'll get a faster response. In my experiments, which I'm going to tell now, I'll be using a gold mesh as the working electrode, counter as well as a gold as the counter electrode, and also use silver wire as a reference electrode. And all these experiments will be done in 0.1 molar tetrabutyl ammonium hexafluorophosphate dissolved in THF. So I said I'll be doing plasmonic semiconductor nanocrystal charging of plasmonic semiconductor nanocrystals. So the material I'm going to do is called copper phosphide. So we all know that copper got two oxidation states, copper 1 and copper 2. So the fact here is that this material, copper phosphide, has some vacancies. These vacancies are generated by copper 2 plus. So if you have just copper 1, it will be just Cu3P. But since we have some copper 2 plus, we don't know exactly how many copper 2 plus atoms we have. It will be 3 minus X. So basically what we do is to synthesize these materials, these nanocrystals, you take copper acetate and you react it with triphenyl phosphate as the phosphorus precursor and heat it up to 250 degrees Celsius in oleolamine. So this oleolamine is act as a ligand. This is oleolamine. It acts as a ligand and also as a reducing agent because it got a double bond, so it can donate that electron. So basically, you'll get a black colored solution after this reaction, which is a colloidal solution of copper phosphate nanocrystals. And if you take the absorption spectra or the excitation spectra of extinction spectra of this solution, you can see that between 1000 nanometer and 2500 nanometer, there is a broad absorption. This absorption comes from the plasmon. In gold, this absorption comes around 500 nanometer, if you guys remember. But here, as I said, because of the free carrier density is between 10 raised to minus 6, 10 raised to 16 to 10 raised to 21, between that range, you'll get the plasmon resonance in the near area region. And if you take the transition electron microscopy images of these nanocrystals, they are quite small, like roughly 5 nanometer. The scale bar is 5 nanometer. And further, if you want to characterize it, we can do the XRD. This is the XRD of bulk copper phosphide, and this is the XRD of the synthesized nanoparticles. So the peaks are matching. So yeah, we basically synthesize copper phosphide nanocrystals. So we need to tune the charge density, or basically we need to tune the charges in the copper phosphide nanocrystals. There are a couple of ways. I said like the ligands bind to the surface, so we can also use the ligands to modulate the plasmon density or electron density and thereby the plasmon. So what we tried first was we tried adding different ligands to these nanocrystals. So basically, in the beginning, we had polylamine and triphenyl phosphate, some triphenyl phosphate. So to this solution, we are adding three different ligands. So we are adding a phosphonic acid, a thiol, and a carboxylic acid. And we made sure that the alkyl chain of these ligands have the same length so that they will introduce the same electronic effect on the donor moiety. So regardless of the ligands you add, I can see that the dotted spectrum is the initial spectrum before adding the ligands. You can see that it's blue shifting. Over time, it's blue shifting. Uh, for all ligands, it's the blue shift is really large for the thiol molecules, but it's very minimum for the stearic acid. So this suggests that there is something happening. And further, there is no change in this, like there is not much change in the color of the solution for this phosphonic acid as well as this stearic acid. But in the case of thiol molecules, when you add thiol molecules, what you observe is the black color solution slowly changing its color and turning into uh, light yellow color and formation of a white precipitate over time. So there is some chemistry happening there with just thiol molecules. So what's happening here is when you when you add thiol molecules, as I said, there will be copper 2 plus as well as copper plus on these copper phosphate nanocrystal surface, also in the bulk. You know that thiol is a soft base. So if it's a soft base, and when it has an option to bind with a hard, relatively hard copper 2 plus and relatively soft copper plus, it will definitely choose copper plus. So it will form this copper thiolate. So it will slowly start abstracting this copper plus from the nanocrystal. You have a lot of copper plus, so basically you will start etching the nanocrystal. The size of the nanocrystal slowly etches. That's why you see, we progressively see a change in the color from black to all the way light brown yellow. And so you form this copper thiolate, and this copper thiolate appears as that white precipitate, which I mentioned before. And one of the interesting properties of this copper thiolate is that they form layered structure, and you can easily detect them using XRD peaks. They show scattering peaks at lower angles in the XRD. So we characterize those white precipitate using XRD as well. So they are copper thiolate. So basically, we are degrading the nanocrystals with thiol. So why do we do this? The reason is because when you make these nanocrystals, ultimately you want to make these devices. So in these devices, uh, when they are separate, these nanocrystals are separate, the response or the charging will be slower. If you want to increase the charge transport between the nanocrystals, you want to cross-link them. So basically, what people, scientists have used so far is they use ligands with two donors. In the case of a thiol, monothiol used here, they basically use dithiol, another thiol here. So it will cross-link the nanocrystals, and the response will be better and faster. So if you use thiol, 4-phosphate won't work. So it will basically degrade. So care should be taken when you are using thiol with copper phosphate. That's why we tried the all these experiments. Anyway, as I said, we will be using electrochemical methods to uh, modulate the plasmon in these materials. And the plasmon comes arise as a result of holes, because you are replacing copper 1 with copper 2 plus. So there is a like loss of electron, and there is an excess hole. So this excess hole is the reason for this plasmon peak. So for charging this material, what we did was first we did a CV. So we started from 0 volt. That's open circuit potential. You can see the uh, this asterisk sign, the purple asterisk sign, and we are scanning in the positive direction. So we are basically oxidizing the nanocrystal and simultaneously taking the spectrum. So here, this is the first spectrum at open circuit potential, and then we are going all the way to 1.5 volt. So we are getting this 1.5 volt, the plasmon peak at 1.5 volt. So the difference is basically it's blue shifting, slowly blue shifting. And then we are switching the potential. We are scanning backwards. We came all the way up to here. Again, back to zero. That's the green one. So at green, it's still blue shifted. Okay, compared to the initial open circuit potential plasmon peak. And now we are reducing it again. We are going to the negative potential where we are injecting electrons. So we are reducing the number of holes. So what happens is like we are going to up to minus 1.5. That's the orange. You can see that it's started redshifting again. Okay, so you are reducing the concentration of holes when you are reducing the nanocrystals. And when you switch back to 0 volt, it's again, it's still redshift and almost came back to the not exactly, but there is slight difference because of the scanning rate. Uh, but yeah, basically when you oxidize the nanocrystals, you are increasing the whole concentration and you are shifting the plasmon to the blue. And the reason for this is because of this relation. This is the plasmon frequency, and it's inversely proportional to the electron density. So when you reduce the electron density, it should blue shift. So this is basically a plot of potential versus the plasmon peak we extracted from here. You can see that when you oxidize, it's blue shifting all the way from 1320 to 1240 nanometer, and when you're reducing it, it's switching back from 1240 nanometer to 1280 nanometer. And if you want to use this for any application, you want to test the stability, you want to see whether this plasmon peak can be modulated at different cycles. So we just tried two different cycles, one reduction followed by one oxidation, and another reduction followed by another oxidation. You can see that the plasmon peak can be reversibly tuned by applying the oxidation and reduction potential. Okay. Other than this, as I said, this is semiconductor. So this material got some band gap. We can also see the changes in the band gap when we charge these materials. If you look at the absorption spectrum, it got, when you oxidize the nanocrystals by applying a positive potential, you can see that the absorption spectrum is blue shifting. That means what's happening here is this is the nanocrystal electronic structure of the nanocrystals at open circuit potential where you don't apply any change. Okay, and when you oxidize these nanocrystals, you are basically removing electrons or injecting holes, and the Fermi level goes down in energy from here to here, and the band gap increases, and you see a blue shift in the energy in the wavelength. And when you oxidize these nanocrystals, what you are doing is you are injecting electrons. So you are raising the Fermi level and you are simultaneously reducing the band gap. So you see that when you apply minus 1.5, which is a cathodic potential or a reducing potential, you can see the band gap, the absorption redshifts. This is because of the in uh, reduction in band gap. So yeah, so to sum up, we have shown how we can charge a semiconductor nanocrystals and modulate the plasmon frequency of these nanocrystals by electrochemistry and simultaneously detecting using spectroscopy. So spectroelectrochemistry has been used here to do that. And uh, yeah, I would like to thank my supervisors, Professor Paul Mulvaney, Professor James Hutchison, and this work has been done by this guy Jianyu. He was he was an honor student with me, and all of the experiments has been done by him. And I would also like to thank Sifich and Dr. Hazen, who also helped me to do some calculations and some experiments for this paper. And finally, I also like to thank the funding agencies. Yeah, that's it. And thank you for your patience and kindly listening to me. If you have any questions, I'm happy to answer that. Thanks. Unfortunately, I can't hear any of what you're saying.
Hello.
I can't hear. Somebody is talking. I can't. Maybe if you got any questions, maybe you can type in the chat. Yeah. No, 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 no. So uncoordinated atoms are there in all nanoparticles, especially when you make them in solution. But they will appear. These localized states will definitely appear.
More confusion between this trap state and conduction band, right? That how we can distinguish this trap state? By which method? Sir, how we can identify these trap states? By which spectroscopic method?
Honestly, it depends upon the trap, and also you can use different methods to identify the trap. For example, in some cases, you can use photoluminescence spectroscopy, especially for quantum dots. People are using uh, using photoluminescence spectroscopy, fluorescence
Hello. Have you done any application level of copper phosphide nanocrystals apart from this?
Yeah, go ahead, please.
Okay, have you done any application level uh, application of copper phosphide?
No. We just made. We didn't do any application with this material so far. We just demonstrated that we can use this material. So the application step is next level. Somebody can do it. I'm more interested in the fundamental side of things. Yeah.
Okay. Is it the copper phosphide nanocrystal? Is it a better semiconductor than the traditional semiconductors that we say?
In what sense? What sense here? What sense? Like better in what?
As a semiconductor?
What property of the semiconductor? The interesting thing about copper phosphide is that when it's in bulk, people say it's not a semiconductor anymore, it's more semi-metal. When it comes to nanomaterials, you have this called quantum confinement effect and it became a semiconductor. I'm not like it's a really better semiconductor in terms of like you should specifically say some applications. For example, if it's if you ask me whether it can be used in solar cells, I don't say no. It's not better semiconductor compared to some of the existing silicon or like higher perovskite. No. When it comes to this plasmonic property, I think it's decent. It's better.
Okay, is it environmental friendly compound? It's phosphides.
Yes. Phosphides are they can react with water and phosphates. They're toxic, yeah. But the same goes for all the materials. If you make a sulfur-based one, it can react with water and form hydrogen sulfide. But again, it's not as toxic as phosphine. It's slightly toxic, but since we are making all these material in organic solvent and with proper encapsulation, especially in our case, we are embedding these material inside a glass. So it will be isolated from water. So it should be safe. Yeah.
Okay, thank you.
Thank you, sir, for your valuable insights. Thank you.
We have now reached the final session of day one. The next session will be delivered by Dr. Sumida, Assistant Professor of PG Department of Chemistry from Annadarsh College for Women, Chennai. I request Dr. Sandhya Jayachandran, Assistant Professor of Department of PG, to introduce the speaker.
Good afternoon. I have been entrusted to introduce Dr. Sumita Annaporath to the gathering. Dr. Sumita is an assistant professor of chemistry at Annadarsh College for Women, Chennai, with over 12 years of teaching experience at the undergraduate and postgraduate levels. She completed her UG and PG in chemistry from Government Victoria College, Palakkad, and earned her PhD from the University of Madras. She has published 12 research papers in reputed Scopus Indus journals and has actively contributed to the academic community as a resource person for various colleges in Chennai. She has attended numerous academic workshops and has presented research papers at both national and international conferences. With a strong academic background and strong research orientation, Dr. Sumita is deeply passionate about teaching and is committed to nurturing scientific thinking and conceptual clarity among students. We are privileged to have you amidst us this afternoon. I request you to take over the session, Subita. Thank you.
Thank you, Dr. Sumida. Now, we will proceed with the Q&A session. Participants can raise their hand to ask questions. Please use the raise hand function available in the chat box. We will take your questions
Thank you, Dr. Sandhya. Good afternoon to one and all present. Hope I'm audible.
Yes, yes.
Yeah. First of all, I would like to thank the management, principal, and head of the department and the organizing committee for inviting me and giving me an opportunity to present my work in this international conference. And special thanks to Dr. Sandhya, who was my colleague, my friend, and my mentor in Anna Desh College. Thank you, Sandhya ma'am, for this opportunity. So today I'll be discussing my work related to fluorophores. I'll share my screen. Please let me know if it is visible or not.
Yeah, ma'am.
It's visible. Yeah.
Yeah.
Okay, thank you. Yeah, thank you. So I'll be discussing my work in the field of fluorophores. Before going into the work, let us understand what are fluorophores. Fluorophores are referred as fluorescent probes or dyes, and these are molecules which are used as analytical tools to investigate the structure, properties, and interactions of biomolecules in various medium. It can be aqueous medium or non-aqueous medium. And these are essential tools that probe the microscopic level of the chemical systems. So, and my work investigates the interaction between one such fluorophore, which is a resocinol-based acridine-dione dye, and biomolecules like adenine, ovalbumin, which is a glycoprotein, using fluorescent techniques, which is clubbed with molecular docking analysis for better understanding of the interaction. And such studies are very important in the field of pharmaceutical industries as they provide crucial insights into pharmacodynamics and pharmacokinetics, which are very much important and relevant in pharma industries. This is a structure of the resocinol-based acridine-dione dyes. One of the characteristic feature of this dye is that it mimics a very important biological coenzyme NADH. And they have absorption range between 250 to 400 nanometer in the UV visible range, and emission takes place around 450 nanometer. Now, based on the substituent present at the 9th position and 10th position of the dye, we can classify them as PET dyes or non-PET dyes. I have taken such two dyes named ADR1 dye, which is PET dye, and the other one is a non-PET dye, which I have calling it as ADR2 dye. In both the cases, the substituent at the substituent which is attached to nitrogen is same, but the one which is at the 9th position is different. And we will see how these minor structural differences brings about changes in the environment, microenvironment in the aqueous medium, and also various spectral properties of the dye. Now, before going to that, what is this PET process? PET process is photo-induced electron transfer process. And let us understand PET process with the example of ADR dye itself. This is the structure of the dye. When the dye absorbs light, an intramolecular charge transfer takes place in the range of 370 to 380 nanometer from the ring nitrogen to the carbonyl oxygen. But at the same time, if there's an electron donating group present at the 9th position, an internal electron transfer takes place to the carbonyl oxygen. And this process is known as PET process. So this is the ADR1 dye where I have a methoxy group present, which is an electron donating group. And on the absorption of light, an internal electron transfer takes place from the methoxy group to the carbonyl oxygen. But at the same time, if in the case of ADR2 dye, there is no such electron donating group present, and because of which there is no PET process taking place. Now, this PET process is an electron transfer which can turn off or quench the fluorescence. We all know as the molecules gets excited, it has to emit back, and that can take place in various forms. And one of the most studied method is fluorescence. So this PET process can turn off or quench the fluorescence. So this, and how does it happen? And now, now if we introduce a guest molecule like urea or any amino acids or protein or any drug which can disrupt this transfer, then the PET process is completely blocked and fluorescence enhancement takes place. But otherwise, what happens is fluorescence is quenched due to this electron transfer. So this property of the dye makes it a very good material for to act as a sensor, biosensor or a probe, which is very important to in the biomedical, biotechnology and medical field. Now let us study or go to the details of these spectral studies, spectral properties. The absorption spectrum of the acridine dye dyes is found to be at 220 to 53, and the maximum lambda max is found to be at 378 nanometer. And this wavelength ICT is assigned to the ICT, that is intramolecular charge transfer, which takes place from the ring nitrogen to the carbonyl oxygen. The emissions data show that when it is excited at 376 nanometer, it exhibits a maximum at 436 nanometer. Now, we can also compare the variation in the fluorescent decay exhibited by a PET dye and non-PET dye. Usually all acridine dye dyes, irrespective of whether it's a PET or a non-PET dye, they exhibit single exponential decay. Now, single exponential decay means they have an homogeneous environment when they are in aqueous medium. That is, one homogeneous of water molecule surrounded by the dye molecule, or you can say the dye molecules are uniformly solvated, leading to a consistent excited state lifetime. Now, how they both differ in fluorescence decay. ADR1 dye have a lifetime of a fluorescence lifetime of 400 picoseconds in methanol and 500 picoseconds in water. But at the same time, the ADR2 dye have a longer lifetime, and it ranges from 8 to 8.5 nanoseconds in water, methanol, and other organic solvents. So in this way, the fluorescence, or you can say in ADR2, the fluorescence decay takes place at for a longer period of time. Now, for the current investigation, I have used absorption studies, emission studies, time-resolved fluorescent measurement, and along with that, some molecular docking studies to get a better insight into the interaction between the dye and the biomolecules used. Today, I'll be discussing two of them carried out by me with my other research. One is the interaction between the acridine dye with adenine. And also, we have tried to compare the interaction of a similar work which was carried out with urea, and that is also a well-established work. Now, adenine, as we know, it is a nitrogen base or a purine base, and it offers a variety of hydrogen bonding functional groups. It is an excellent non-fluorescent solute and provides 5 hydrogen bonding sites, out of which 2 are its donor sites and 3 are acceptor sites. Out of these 5, the position at N6 and N7 are the most active sites for hydrogen bonding. When we add adenine to acridine dye, PET dye, we didn't find any change in the ICT absorption of the ADR1 dye. So that shows that the ground state property of the dye was not affected by the solute. But at the same time, when we recorded the emission spectrum, we found that initially there was a decrease in the intensity, but on increasing the concentration of the adenine, the intensity of the emission increased, or leading to a fluorescent enhancement. Apart from that, we also observed a red shift. Now, this fluorescent enhancement and the slight red shift observed can be attributed to the hydrogen bonding interaction, which we can further validate with other studies. So to understand the interaction in a better way, this is a schematic representation of ADR1, that is PET dye with adenine. The dye absorbs the light, ICT process and the PET process takes place. Now to this system, when we are adding adenine has got various possibilities to combine with the dye. It can bind with the methoxy oxygen. It can bind with the carbonyl oxygen. It can bind at the NH position. But it has been shown by quantum mechanical studies or energy minimization studies that the adenine does not prefer to bind at the methoxy oxygen. That has been established by the quantum mechanical studies. Rather, it prefers to bind with the nitrogen, binds through hydrogen bonding to the NH group or the carbonyl oxygen. At the same time, the system has water also. So water is a possibility for water also to bind through hydrogen bonding. But again, the same quantum mechanical studies show that water does not prefer to bind here, and rather it prefers to bind with carbonyl oxygen. Now, why does this happens? This is because when adenine binds to the NH group, it forms a more stable complex than when it binds with the methoxy oxygen. So based on these energy stabilization studies, we were able to understand that adenine prefers to bind either at the carbonyl oxygen or at the NH position. Now, this bathochromic shift or the red shift which was observed in the emission study is due to the hydrogen bonding at the NH hydrogen, and the adenine molecule, which is also bonded at the carbonyl group of the dye, is not in a position to suppress the PET process because of the geometrical constraints, because for a PET process to be completely suppressed, the guest molecule, here in our case adenine, should be able to reside between the donor and the acceptor moiety, which it does not happen due to geometrical constraints and also due to the stability. So the PET process is not suppressed effectively, which leads to a slight fluorescent enhancement. So if it was completely blocked, there would have been a massive fluorescent enhancement, but we have observed only a slight fluorescent enhancement in this case. So we can say that suppression of PET process is less effective when compared to other molecule. But at the same time, when we had carried out the similar study with urea, it was found that PET process was completely blocked and there was a much better fluorescent enhancement. To understand the binding nature or stoichiometry, we plotted Bense-Hildebrand plot, and we would able to see that the dye combines dye and adenine had a 1:2 binding interaction. That is, one dye binds with 2 adenine molecules. So you have a dye forms a 1:2 complex with the adenine, and the binding constant value was also calculated to be found to be high, around 694.6, and at the same time, the urea our dye was able to form only a 1:1 complex, that is one dye molecule binding with one molecule of urea. Constant was also found to be very low. So from this we can understand that the dye prefers to bind with adenine and form a more stable complex than forming a complex with urea. Further, again, to emphasize on the stability of the dye-adenine complex, we measured the fluorescent intensity of the dye-urea complex in the presence of adenine. That is, we added adenine at various concentrations to a diurea system. And we found that with the increase in the concentration of adenine, the fluorescent intensity decreased, which shows that adenine was able to effectively displace the dye molecule from the close vicinity of the urea and itself binded with the dye. And such, it resulted in different microenvironments. Microenvironments means you have one dye binded with adenine, two molecules of adenine. A dye can also bind with water molecule. Dye can also bind with urea. So they all form small different microenvironments which will have different fluorescence lifetime. Now to understand that, we have a schematic representation. This is a system, diurea system, which the blue color shows urea water system. Along with that, we have diurea system and urea interactions also were there. To this system, we added adenine, and successfully adenine was able to push away the dye from the close proximity of the urea, and that led to the formation of various co-spheres, or we can say the dye was surrounded by water in one of the co-sphere. It was also surrounded by adenine molecules, and another co-sphere we could find some urea molecules. So several such co-spheres were formed in the aqueous phase. Further, we carried out fluorescence decay of ADR1 dye, and the single exponential decay of the dye changed or transited into a bi-exponential decay, which shows that the environment around the dye has changed, or you can say that there were presence of multi-environment in the system. And also the PET component, it shifted from 490 to 550 picoseconds. The short life, that is, shows that PET was gradually suppressed. And also the data also showed that there was a new lifetime which was generated, and that is due to the formation of new micro environments formed in the system. Another work which was carried out was similar work which was carried out was with ovalbumin, which is a glycoprotein. This ovalbumin, we know it is a egg protein which is found in avian egg white, and also it is belongs to serpent family with a huge molecular weight. It is rich in amino acids like glutamic acid, aspartic acid. It possesses various biological activities like anti-cancer, anti-hypertensive, and it is also present in significant amount in various vaccines like yellow fever, influenza. So again, ovalbumin is a biologically important protein. Ovalbumin was treated with ADR1 and ADR2 dyes. The absorption study or absorption spectrum of the ADR1 dye in the presence of ovalbumin again showed no change in the ICT absorption. That is again telling that the ground state is not affected. But again, the emission spectrum, we could see a red shift or a bathochromic shift, and which exhibits that there is a formation of various formation of microenvironment in the medium. But surprisingly, no such changes were observed with the non-PT dye, ADR2 dye. There was no significant change in the fluorescent intensity. There was no shift towards blue or the red region when ADR2 was treated with ovalbumin. And such changes in the excited property or excited state property of the dye is due to its structural differences. This is a schematic representation of ovalbumin with ADR1 in aqueous solution. Ovalbumin, you know, it's a large protein, so it will have various domains, or it will provide various domains where dye can go and occupy. and dye occupies those spaces or domains and interacts with ovalbumin through hydrogen bonding through any of its amino acids available. And it binds to the dye in such a way that fluorescent the PET process is completely suppressed and fluorescent enhancement takes place. So here again it is a hydrogen bonding which plays a major role here. Time-resolved fluorescence spectral studies of ADA1 dye with ovalbumin showed that the single exponential decay of ADA1 dye changed into multi-exponential decay. And this shift from single to multi-exponential is due to introduction of the protein to the system creates several distinguishable microenvironments around the dye molecules. And similarly, the PET component tau1 increased from 490 picoseconds to 740 picoseconds. That is, PET process is completely suppressed. And apart from that, we were also observed, the data also revealed that two new lifetime components were also formed, tau2 and tau3, which is again due to the formation of different microenvironments. And those microenvironments were formed because dye resides in different domains of the ovalbumin. One interesting factor which was found is that there was no free dye component present. That is, dye was completely trapped in ovalbumin. Now that was understood by the increase in the PET component. If the dye was free, there would have been the lifetime would have been 500 picoseconds or 490 picoseconds, but it gradually increased to 740 picoseconds. So that shows that dye was completely trapped inside the ovalbumin, or we can say dye was completely interacting with the ovalbumin. Now let us see what was the case when we introduced the protein to the non-PET dye. Here, the single exponential decay changed to bi-exponential decay with two different lifetime components. So here, the values can show that the lifetime is quenched. You can see from 840 picoseconds, it reduced to 790 picoseconds. So here the lifetime is quenched or reduced, or you can say ovalbumin act as a quencher here. It behaves as a quencher, and so that was totally different from what we observed in the PET dye. Further, to validate our findings, molecular docking studies were carried out, and with the help of those theoretical studies, we were able to calculate the energetics of the dye protein complex. So we generated 10 conformers based on their stability between the PET dye and ovalbumin, and various other parameters were also calculated: binding energy, ligand efficiency, inhibitory constant, etc. And based on these values, we found that one particular conformer was the most stable conformer. This is the ADA1 ovalbumin molecular interactions. We can see that each conformer generated interacted with various amino acid residues present in the ovalbumin. And it's not that dye will specifically interact with only one specific amino acid moiety. No, it interacts with various amino acid moiety available to it. And we were also able to find various hydrophobic interactions present apart from the hydrogen bonding interactions. This is a 3D and 2D conformations of the most stable and the least stable conformer. This is energetic. Similar study was carried out for non-PET dye also with ovalbumin. And again, we generated 10 conformers for the dye protein complex. This is in the decreasing order of their stability. And here, this also gives you the di-ovalbumin molecular interactions. Here also we can see that di interacts with the available amino acid moiety, whatever is available, and along with that there were hydrogen bonding interactions as well as other hydrophobic interactions with the amino acid moieties. So the 10 conformations of ADA1 di and ADA2 di with the ovalbumin suggested that the di does not prefer to bind with only one particular amino acid residue. It binds with the various amino acid residues. It can also bind, it can go and occupy deep inside the ovalbumin or hydrophobic region, or it can also bind to the exterior part of the ovalbumin, which is more hydrophilic in nature. And such similar type of binding was observed in the case of ADR2 di also. So to conclude my work, I can say that acridine dione dyes are highly sensitive and effective extrinsic